Hello, hello. How does it work? My screen. Okay, yeah. So before I went, talk about the syllabus and where we are and today's goals and all that, just wanted to show an example of what's the, I guess, news for this week or news for the past day or two. Is this new paper, a new research work, which will, today's lecture is not going to capture this completely, but you could use the model from today to also do something similar. Although the model from next lecture, this transformer architecture, which is the kind of the backbone architecture for ChatGPT and Gemini and all sorts of language models. So that's the one being used here. But I just wanted to show you because this one was published yesterday. So if you click on that link here, paper goes to this page, and you can see when it was submitted. It was submitted yesterday. It's called World Model on Million Length Video and Language with some ring attention. Okay, so there are a lot of words here. So they're calling something as a world model, rather than like a text model and a image model. So world model for them, it just means text and image combined model. Okay. Million length corresponds to the sequence length. Okay, so today we'll actually do a lot of sequence-to-sequence modeling. So there's a notion of a sequence. So text, for example, a sentence is a sequence of words. Now you can imagine a million length sequence of words. It doesn't have to be words, what are called tokens, but it's very long, and they can use that much of input to produce an appropriate output. And so it says video and language model. So they're not just working with images, they're actually working with videos, videos are just a sequence of frames. Okay, sequence of frames. Frames are nothing but images. Okay. And they have some innovation, something called ring attention. So we will not get into the detail of what a ring attention is, but we'll look at attention today. At least the last part of today's lecture, we'll look at attention. And actually next lecture, one of the core ideas of transformer architecture in the next lecture is this notion of attention also. So today there's going to be some attention. Next lecture also there's going to be some attention. Both have kind of same informal idea, but in terms of the neural network architecture, they're going to look different slightly. But this was I just wanted to show you this because this might be one of the biggest models. So in terms of like this tokens and so on. So actually, let's see. So I mean, there's a lot of text in this, and large world model.github.io is link. So they're saying that we train one of the largest context-sized transformers, which we'll see next lecture, on long video and language sequences, setting new benchmarks and difficult tasks. And what do they mean by difficult tasks? Okay, so they also give open source models, okay, at certain size. But what do they mean by that, right? So this is just an example, and we'll stop after this. Is basically they're trying to do question answering over a 1 hour video. So given the video is an input, and then you prompt. Your prompt is basically a question, hey, what's happening in the video? And not as general as that, but what vehicle was the person dressed in the T-Rex costume riding? Okay, and then you ask GPT-4V, which is one of the really capable models today. The answer is not an answer. Gemini Pro is also wrong. Video Llama model. So Llama is a collection of models by Meta. research, and then VA is for the visual part as well. So many of these models can work with vision. So it's not GPT-4, but GPT-4V. So they can work with images and videos also, in addition to text. And then they have this large world model, which at least for this cherry-picked illustrative example, produces the right answer. Okay. So just to give a sense of what they are trying to build, trying to build really in just like another data modality, which is videos. Okay, videos are also sequences of some data. Doesn't have to be words, but sequences of images, and images, as basically have vector representations, image encodings. That's exactly what they do. In fact, in their figure, they use some model, VQ-GAN, and we'll look at what is a GAN in 2 lectures from now. But they use this to create some vectors, just like we can create vectors with text, and we'll kind of get into this details. Maybe not this architecture, because this is like really advanced research, but we'll look at the basic building blocks of these ideas. This one definitely next time. So hopefully next time it will be a little bit more clear what is going on here. But today we'll look at some other, just understand what is sequence modeling, and then look at a different family of models called LSTMs. Yeah.
So very basic. So what is the difference between token and like
a word?
Whenever we use like vectors. So.
No. So these tokens are so these are actually so tokens. We have only talked about text in the lecture. So text tokens are, just think of them as text words. So although tokens are considered subwords, so just parts of the word are also considered tokens. So tokens are still symbols. They still need to be mapped using embedding matrix or something equivalent to that, something like a word2vec, to get to a vector. So tokens are not vectors themselves, but tokens are like words. And so for every token, there can be vector representation. Yeah.
And like, what is the reason why, like, usually when I read up about this, they say the rate for like using the API is like some dollars per 1,000 tokens.
Yeah. That's what.
Why not string?
Because that's their base unit. So they either they have to handle the complexity of words to tokens, like how many tokens and how many words, or they can just say, okay, we'll just work at the level of tokens and forget about it. I mean, as in the end user will have to worry about it. Actually, they say here, right? So generally you will see that, for example, if you use an API like OpenAI's API, I don't know how many tokens it is today, but something like, I mean, they price things at the level of price per token, price per 1,000, a price per 1,000,000 tokens. That's just how many tokens are going in, how many tokens are going out. But also, there's a maximum length of the number of tokens that you can actually even input. Like if you input more than that, it will be discarded, as in it cannot be processed, right? So the maximum length, I think, is like 4K or 16K or something. These are like some of the bigger models. In fact, 2-3 months ago, it used to be 2K or 512 as the max length of the number of tokens you can input at any given like inference situation. But yeah, so dollars per token is a metric that many of these have used, because that's the input. Really, that's the level of input that the models consume. Yeah. Even if you have words, like a word could let's say if it's a short 5-letter word or 6-letter word, it could lead to 2 or 3 tokens. So whether it's 2 or 3 influences how much processing needs to be done, because all the processing is at the level of token to a vector and then passed on to a downstream neural network. Yeah. Okay, this was just about that. Now let's actually get back to our notes. Any questions here? So I think I missed wanted to capture a couple of things. Firstly, syllabus. So where are we, right? So we are here. I think it's the 6th lecture, and whatever we'll cover today, and hopefully I'll try to insert assignment 3 related comments within this. So my plan is first to cover the material, which is actually, can be covered, within our allotted time, and maybe this last part we can spend a little bit of time on assignment 3. Okay, so because I think doing that in an inverse order will require a lot of explaining. And anyway, let's do the explaining first and then look at assignment 3. And more importantly, so that's assignment 3. Assignment 2 is yet to be graded, but I'll grade it soon and get back to you guys. But the next milestone is actually this report, which is due on the 5th of March. And it's not that far, it's 2 weeks. Yeah, with 3 weeks from now. And it's this milestone is important because right after that milestone, we'll have a debrief with each team. And around that time, I'll let you know how we're going to have it. But it's mostly potentially we can make it online, and it's just going to be team specific interaction with me, and we'll kind of go over your project. It's a big component of this course, so it's important to start slowly thinking about at least the domain, at least the something that you want to investigate. Have some candidate ideas. You'll see that one of the big restrictions that will come from one of the big restrictions that will constrain your efforts is going to be compute. Google Colab can only do so much, and even Colab Pro can only do so much. So, like for example, this large world model, it's not an easy thing to train and all that. You can probably run inference on it, but those types of things are kind of out of scope. Okay, so what is the goal for today? So we are exactly 1 off in terms of lecture. So let's lecture 05 is, let's say we are just doing zero-based indexing. So lecture 5 is like the 6th lecture. And today we're going to look at recurrent neural networks and transformers. Transformers actually next time. So anyway, we'll look at recurrent neural networks. In particular, we'll introduce sequence learning, RNNs, and LSTMs. Okay, these are acronyms for now, but hopefully during the session, you'll be clear on what is an RNN, what is an LSTM. And by this time, you would have seen like all the models that we've seen so far. We haven't seen too many models. Convolutional neural networks, feed-forward networks. Mostly we understand in terms of a forward pass, because once we understand the forward pass, we know how to write, let's say, its definition in using PyTorch or something. The backward pass, the backprop, and other behind-the-scene details, which are very important, are kind of mechanical. So we don't focus on the training and the optimization aspects of these models, although it's a big component in reality, which is where you will probably have a lot of challenges in your projects and stuff. But lecture 5 and all the other lectures, we'll see that the pattern is going to be, we're going to only focus on forward passes, as in like, okay, given an input, how are we going to process it to get a score vector or whatever we are trying to produce. Okay. Let me not talk about assignment 3 yet. Lecture goals, right? So goals basically are, when can prediction tasks have sequential dependencies? Actually, a lot of prediction tasks have sequential dependencies, but a lot of them don't. Okay, so what is sequential dependencies? For example, if you think of the canonical machine learning problem, like for example in 575, let's say you have tabular data. There, the rows of the data are an example pair, input-output pair. The rows can be permuted in the table, and it's not going to influence anything, in the sense that there's no sequential dependency of row number 89 and row number 90 and row number 91. Okay, there's no dependency on those X values, for example. They could be permuted, they can be shuffled. It's still okay. And in fact, even in our first lecture, when we looked at review of classification, our data pair, our loss function was symmetric, is in the sense that loss function was a loss over each example, summing it up. So you can see that example ij, if I change it to the last example and last example becomes ij, it doesn't matter. It's at the end of the day, both contribute to equally to the overall loss, and the backdrop happens. Okay. So what I'm trying to say is that there are many problems where there's no sequential dependence once you curate the data, but there are many problems where there is sequential dependence. Given that, we want to exploit the sequential dependence. What are some models to do that? There are some classical models, and in fact, there's a whole field of time series analysis which looks at sequential dependence. Okay, especially with the huge applications to finance and weather forecasting and many other health forecasting and so on. But we look at neural network-based models. One of them is called the RNN model family, or the recurrent neural network family. Okay, so we'll kind of revisit this acronym and its full form again and again. And then a specific variation of that RNN family is called the LSTM model. Okay, so RNN and LSTMs are not different. LSTM is a type of RNN. Okay, just changing in the definition of the model a little bit. Okay, but still works exactly the same way as any other RNN. And then we'll look at some applications as time permits. And while doing so, we'll also look at the notion of some notion of attention. Okay, I know in the paper there is ring attention, but we'll not look at ring attention because they just introduced it yesterday. We look at something called encoder decoder attention. Okay, so now the words don't make sense. What is encoder? What is decoder? What is attention? Doesn't make sense yet. But when we get there towards the end, if you have time, we'll cover that today. If not, early next week. Sorry, early next lecture. So that's the plan. So by the end of the session, at least appreciate what is sequence learning, what is an LSTM, what's an RNN. Okay, and we do want to reserve some time for assignment 3, just discussion briefly. Okay. Okay, I can just use this. Yeah. So we'll actually jump into the topics. RNNs are just recurrent neural networks. LSTMs are long short-term memory networks, LSTM. And they're just a kind of variation of RNNs. It's not really based on RNNs. They're just a variant of an RNN. Okay, they just, you can literally replace in PyTorch if you're defining an RNN. If you're using an RNN block, just like a conv block, convolutional conv2D or something like that, you could use a nn.rnn as a block, and then you can replace that with an nn.lstm, and it'll, everything will work, right? And we'll look at sequence learning. So let's actually get started. So what is sequence learning, right? So on the left side is the most familiar example for our machine learning problem, which is what I was discussing in lecture 1. The leftmost side is what we've discussed, right? So there's a fixed sized input and a fixed sized output. Like, for example, we have a 10 class classification, CIFAR 10, and we have a fixed size input, the 32 cross 32 cross 3 size image, right? So that image classification problem is a there is no variation in the size, in the sense that any new test instance, there still has to be the same sized image, and there still has to be only 10 classes. You can't change the classes, or you can't randomly change the input, right? Now, everything else that you see in this diagram has variable length inputs or variable length outputs. So you can see that, for example, image captioning is a problem where image is an input and the computer has to say what is the image about. Okay, in that case, what is the image about? It cannot be a single word. Maybe that's too restrictive. So you may want to capture, what is the image about in a variable number of words. And so that is a problem which requires. This green thing here is not explained in this slide, and we'll explain what is the green thing, which is actually a sequence model. RNN can be a sequence model, can be other things. We'll explain the green stuff today. But this is a fixed size image, sorry. Or a fixed in terms of dimensions, and the output is a variable number of words. And same thing, the opposite side is something we've already done before, which is sentiment analysis. With CNNs, for example, we said, okay, it's a matrix. The matrix can have an arbitrary number of rows, right? In a CNN-based sentence classification. So variable number of words leading to one or one fixed size class, like a positive or a negative sentiment. And then you have two variations where the only difference is, like, when do you start producing the output? In one version, you start producing the output after you've seen all the inputs. And in the other version, you start producing the output immediately. But in both versions, the input and outputs, the number of inputs and number of outputs, is a variable length in every example. So example ij and example xiyi and example xjyj, they could be a variable length. So for example, in one case, sentence could have 5 words. The other case, a sentence could have 10 words, and the output sentence could have 15 words. The other case, 20 words. So the examples here are written as machine translation and video classification. So it's just examples. So hopefully this high-level diagram of the types of nature of these problems are clear. Okay. Any questions here? Because if you're not understanding this, then there's going to be because we're going to now talk about what is this that we can build here to handle this variable length, okay, across examples in my training data. So our training data is no more like a table. If you think of a table, a lot of empty values. Okay. In fact, our inputs are not even like single numbers. It's not this 3 things don't correspond to 3 numbers, but these 3 things correspond to 3 embeddings potentially. If it's a word, then word embeddings, because there are 3 words perhaps. Yeah. So a brief comment or remark about the idea of persistence or this dependency across words in a sentence. Okay, so it's not across examples. I know earlier I said there is no dependency across examples in the first setting, right? So the review that we did in the first lecture, example ij and example ii, xi, yi, and example xj, yj, they're not related. You can permute them, doesn't matter. Here, by persistence, I mean persistence across these words. Okay, if it's a sentence, clearly all the words in the sentence kind of influence each other. For example, if you're doing a language model, so all the previous sentences, all the previous words influence the determination of the next word, right? So that's the persistence I'm talking about. Right. So feed-forward networks and CNNs, they don't explicitly model persistence unless you explicitly add something. For example, if you're classifying a scene in a movie, then input size is fixed and output size is fixed. But what if you wanted to make a CNN variant where you kind of look at previous frames also, previous images also, kind of determining the current class? Okay, that would be something where you want to capture persistence, right? But if you're only looking at a fixed number of previous frames, then it's still, it's nothing. It's not sequence to sequence modeling, because if it's a fixed number, then it's a bigger tensor as an input. Okay, it's not really sequenced. So architecture. So I'm going to introduce a solution to capture the sequential nature, persistence nature, through a model called RNN. Okay. So how does it capture persistence, right? So we're going to start with a base network. Okay, we'll open it up in a second, but A is a base network, which now has 2 inputs and 2 outputs. Okay, so it takes the little teeth token, or I know we're using the word token, but the teeth input element in that sequence of inputs, and produces n output, which we're calling it as HT, which is a teeth output for the same example. Okay, so this is the variable length input, variable length output situation, and we just want to say that in that variable length input, let's take the teeth element of the input, and pass it into this base network, and we'll get some intermediate output. It's not the final output yet. And then there's also going to be another output, which is going to be fed back into the same network. Okay, this seems like some sort of circular thing going on. It's not. It's just a notation convenience. This is the representation of the network. When people call recurrent neural networks, this is the actual network. It's just there's no kind of cycles anywhere. So backpropagation and all that, makes sense. So basically, it's the same base network replicated, the same weights being same function being applied many times. Think of it that way. So now you can see there's a sequence of length x, t plus 1 or equivalent. Then first you input the first token or the first vector or the first word, produce some intermediate output, input the second word, produce the intermediate output, input the third word if you want, produce the third output, and so on. Okay, but while producing the third output, you see that there's the second output is needed, and second one also needs the first one's output, right? So there is this dependency across previously seen words in that example. Okay. And this sequence is useful for working with this structure, this type of function evaluation, right? So if I have a variable length input for this ith example has t length input, little t, okay, t or t plus 1 length input, versus maybe jth example has maybe 2 times t number length of input. Doesn't matter. For each example, we evaluate. We pass each one and use A to kind of generate the outputs per example in its own. We adapt the number of A evaluations by how many ever vectors there are. So how many ever words there are in that example.
So what goes into the second one from the first? Is it A or it's not a?
What is this arrow? All these arrows actually correspond to just vectors. So what goes into A is a vector. The first one, just think of it as 0 vector going in. because that's the beginning. But these are just vectors, some processed outputs. In fact, in the RNN, it just turns out that the same H0 is just passed as a output to the next evaluation. Okay. What are we trying to do, right? We are just trying to capture the notion of persistence. So somehow some previously computed number should be useful for me to make a determination now, right? For example, think of the example sentence classification, but under this model. We have done sentence classification before with CNNs in the previous lecture. But if you're doing sentence classification, let's say there are two sentences. One is length 10, one is length 20, right? So the length 10 one, we're going to do 10 such evaluations where the first word in the sentence, second word in the sentence, third word in the sentence, 10th word in the sentence, all of them are input. But while evaluating the second word, we also get some bunch of computed numbers, some transformed bunch of numbers that will influence the current output, which is irrelevant for us because we are doing sentence classification. But maybe the last one, which depends on all the words, maybe that's the one which should produce the score vector, which is the classification, which is maybe the positive or negative sentiment of that sentence, right? So it's just dependency across the individual elements of the sequence that is being captured here. Okay, in a particular way where the same base block is being reused again and again and again. Okay. Same thing if you had a collection, if you had a video, you had a collection of images. Each one, a video is just a collection of images, frames. And if you had a predetermined CNN, which is embedding that frame, then you would have just a vector at each location, right? And then given each of those embeddings, maybe all of them can be used together to maybe classify the video as having an anomaly or not, or like maybe having some object of interest or not, for example, right? So same architecture works. Yeah. So what are these, right? So the block A will have parameters, right? So here I'm just showing that as parameter theta. So each of these timestamps, or it's not really time, but whatever the second word, third word, it's not really time, but some index, right? We're going to call them in a stage, and each of these, each of these blocks, it seems like, okay, there are several number of blocks, but all of them are driven by the same parameter. It's like we are applying the same function again and again. So if you think of a PyTorch module, it's like inside the forward function, there's a for loop saying for I is equal to 1 to 10, just apply the same layer again and again. So we are not having 10 different thetas or 10 different parameters. It's just the same parameter. It's the same block. Okay. It's like instantiating nn.linear once and then calling nn.linear like whatever number of times is needed depending on the input length. Okay. So, okay, since we saw the picture, so we're going to use this notation. Try to keep it consistent throughout the slides. So a block, yellow block is a neural network layer. Okay, and we'll see. In fact, in today's lecture, we'll see the instead of looking at ReLUs, we'll look at sigmoids and tanh functions for nonlinearity. But there's just historical origins, and that's what the community settled on for those. We'll look at this. This is for just a vector, as I said, vector going from input to output. So we're going to use this notation to say vectors are concatenated. Concatenation operation, if you remember, 10 length vector plus 10 length, not plus, but 10 length vector concatenated with another 10 length vector. It's going to be a 20 length vector. And here is just a copy. The same vector is going to two different locations. Okay. So here is what we're calling as vanilla RNN, like the most canonical RNN, the simplest thing, where the A block, now we opened up the A block. We have zoomed in, kind of enlarged the A base network. And in fact, this is what is defined as a vanilla RNN in the literature. Okay. So what is this network? You can see that XT is concatenated. Remember, this operation means concatenation, right? So XT is concatenated with HT minus 1, okay, together. Now you have a little bit longer vector, and that's going through a neural network layer. Remember, this yellow block, rectangular block means a layer, going through a neural network layer. With the word tanh means that, once it goes through the layer, there's a bunch of output neurons. Those neurons, each neuron has a nonlinear activation function being applied to it, which is a tanh operating, tanh function, which we know is exactly like a sigmoid, but it's centered such that at 0, the value is 0, and large negative values, it's -1, and large positive values, it's 1. Okay. It's like an S, basically, elongated S. And then whatever is the output, it's produced as an intermediate output, but also pass as the input to the next computation if needed. Okay, so this is a definition of a vanilla RNN.
I have a question. So, since you said that each layer will be same, right?
There's only one layer in this base network. This is a base network, but it's just definitely one layer.
For xt and xt-1, both layers will be the same, right?
Xt and xt-1. No, first, so you have to process your data sequentially. It's a sequence. You have a sequence of words. Let's say you're doing sentence classification. You have a sequence of words. The t-1th word is whatever the vector representation is passed in first with some t-2th ht that passes through this network. It has some weights w comma b, right? This is a linear layer. Okay, there's some w comma b. There's some output that's generated. Now that output, when it's generated for the next stage, there's a new word. Its vector representation is passed in, concatenated. Again, the same w comma b is used. That's all.
Yeah, so exactly, that's my question. So the same weight has been passed on.
Yeah.
Then how will it generate different results than what it generated in the first?
Yeah, but the input, this is different potentially.
Yeah.
The same way, this is different, and this could also be different, right? So all the action is in the inputs being different. Most of the action is in inputs being different. Yeah.
Sorry, yeah.
It's the same weights. You're saying, okay, with the same weights, how can the outputs be different? I mean, if the inputs are different, the outputs could be different.
Yeah, but for the first part, which we concatenate.
Concatenate, yeah.
Sorry.
Yeah, we concatenate these two.
That. So since the first part,
yeah,
it's already been processed through the same way, right?
Yes.
Suppose it's ReLU. So if it was not 0, the output should be the same for the first part, right?
No, the first part is not gonna remain the same again and again. It'll be different vectors. So it's a tanh, but even if you think of ReLU, this ht-1 is going to be different from ht, and it's going to be different from ht+1 for sure. I mean, it's very rare for them to be same. I mean, it's like it's easy to generate an example where they're different. Very hard to generate an example where they're same.
I also want to ask one thing.
Yeah.
Like we have tanh activation function in the second block.
Not just second block. So we just opened up this. So it's all A blocks. We just opened up the center one, but it's the same exact same pattern.
Only, or
yeah,
they could have different
tanh.
But is it like we use tanh only every time?
Yeah.
In a particular series, like the same activation.
Yeah.
Or it could be different.
I mean, people just use the same. If you want to define a different one, you can. Yeah. When I say people, actually, let's look at it, right? So here is RNN block. So it turns out, just like nn.linear, there's an nn.rnn block in PyTorch. Actually, let me first cover the example here, which is based on NumPy, and then we'll get to PyTorch. So actually, this right after this slide is a simple representation in just using NumPy, just to see like what are we talking about, right? Just to kind of make it as concrete as possible. So here's an init function, which is just I need as I said, there's a tanh block, linear layer block. So there has to be a weight and a bias, right? W and B. Those are kind of defining the linear layer. And then I also need to remember, right, what was the previous H? I mean, somehow I need to remember because I need to use it for the current computation. So just think of this like temporary variable where I remember like what was the previous H I computed so that I can reuse it. And then your stepping is every time you get a new XT, you remember the previous one, you just do a head stack or horizontal stack, or basically the concatenation operation of H with XT, HT-1 is XT, and then just multiply with W, right? And then add bias. Okay, that is WX plus B, W, whatever, elongated X, concatenated X plus B, and then you do a tanh operation on it. And that's the hedge. You return that, and you also save it locally in your, in your local variable so that it can be used next time. Yeah. Whose dimension? No, it doesn't, right? So the dimension of the vector is just dependent on what is the number of rows of W. Right? Even though we concatenated, the output is still going to be the same dimension as the dimension of H. Okay, so the number of, you can think of rows of W as like, let's say 10, let's say the columns of W are 15. then H may be 10 and like XT may be 5. So even though there is a 15 length input coming in after concatenation, it's still a 10 length output coming out for the next use.
W is the big.
W is the parameter of your model, RNN model here. So W is the thing for which explains the yellow block, right? So this W is the W comma B are the parameters of this linear layer. Yeah.
Like you were saying the example number of rows and number of columns. Can you please explain it again?
Yeah, so I was just saying, he was just asking if you concatenate, maybe the output is gonna keep blowing up, right? So what I mean by that is, let's say H initially was 10 length of 10 dimensions, 10 dimensional vector, and XT is always 5-dimensional vector, let's say, or embeddings are 5-dimensional for simplicity. So it's 15, right? So if you concatenate, it's 15 length. I'm just saying that W should have a number of columns be 15, number of rows to be 10, let's say. Then you still generate a 10 length vector, right? So next time when you use, you still have a 10 length vector, and then again you get a 5 length new input, but you still keep the dimension the same. That's all we were discussing. Yeah. Any questions? Puzzle looks or not?
Yeah.
Yeah.
If you can go back to slide number
12.
So the one output is XT minus 1, and the same we have concatenated with XT.
Yeah,
So,
in the vanilla RNN, it turns out that although it's supposed to be a 2 output base network, the 2 output is just the same. It's the same vector. Yeah.
But XT, like the output is just the output of the activation function, like the processed weight and biases.
Yeah, it's just
like
calculation. Yeah.
Proper output.
Yeah. So what you do is with this HT, you will apply another linear layer to get to the score vector. Let's say you're doing classification, binary classification. Then first of all, if you're doing sentence classification, you don't need all this HT minus 1, HT and all that. Once the last word you have processed, the last word's HT, let's say, that HT is whatever length, let's say again 10 length. Let's say you're doing 2 class classification. Again, you have to apply a W comma B so that you can actually come back to 2 scores, one for the positive sentiment, one for the negative sentiment. So there's one more linear layer that is needed. Yeah.
But here it's just the processed weights and biases that we are adding, or maybe concatenating with XT.
Yeah, this is just the base operation. That's the intermediate computation for the RNN part. But to complete the classification picture, you need a further output layer as needed. Yeah. We'll see that actually in a second. I just wanted to show this, and then you can instantiate an object from this class with, let's say, I mean, here actually it's not 10 and 5, it's 3 and 4. So if you have a 5 length sequence, then you can just, understand engineering XT. You can just give the XT, produce the HT, and then keep printing HT or returning HT, whatever you want. Yeah. This is just to show like how do you code up a simple RNN forward pass using NumPy. I'm trying to think whether I should jump to the code or not. I mean the PyTorch or not, or do an example first. Let's do an example first because it has illustrative numbers, so it's kind of just wraps up the if there's any gaps you can close it. So here's a language model just to kind of mirror the other language model that we saw last time, which is two lectures ago, which is the Markov-based language model. It was actually a character level language model, but it's a language model. A language model, if you remember, people use this heavy word, but it's just a simple model which takes a variable length input or single length input, whatever. In Markov case, it was just 2 previous characters to predict the next character. But you can imagine a language model in general, given the previous words, should be able to predict next word. Okay. So given previous words, predict the next word is a language model. And in that language model, you can say, oh, what are the previous words? How many previous words, right? You can say, oh, I can consider all the previous words. Then how many previous words there could be, right? There could be 2, there could be 5, there could be 100. But given all that information, can you tell me what the next word is, right? So that's the more general version of a language model. Markov models have fixed inputs, right? Fixed conditional, things, evidence that you're conditioning on. So in fact, this is actually the problem in your assignment 3, question 1 also. So let's look at this. So if you have a large text corpus, then you can actually model the probability of the next character or the next word given the previous characters. Actually, we'll look at the character level only because just to kind of keep it consistent with our previous character level Markov model. Okay, generally language models are used to generate new text. Okay, and you need to build a little bit more machinery on top of it to be able to answer respond like a chat version of GPT, for example. So GPT by itself is just a language model, but chat GPT is a chat version of it, which has been tuned to kind of respond to answers. Okay, there's a slight difference between them. So let's look at the illustration first and then get the code. So again, same, let's look at one example sequence, HELLO. Okay, hello is the sequence. And in our case, let's also say that our vocabulary is only 4 characters, H, E, and L, and O. There are only 4 characters. So if there are, if our training example is HELLO, and we're training a language model, we're not doing sentence classification anymore. Okay, which means that we actually, for this training sequence, we actually have 4 training examples. Why? First character should predict the second character. So given H, I should predict E. And given HE, I should predict L. Given HEL, I should predict another L. And then given HELL, I should predict O. Okay. Unlike a sentence classification model where given an arbitrary length sequence, I should only predict some binary class, for example, positive sentiment and negative sentiment. It's a little bit different. Okay, so let's say we also have, since our vocabulary is only 4, let's say we embed them into just by using one-hot encoding. So no word to vec and all that stuff. Anyway, these are characters anyway. So let's say we just get a 4-dimensional vector. So here's an illustrated picture for this example. So for this example, H is encoded with a 1 here and 0s everywhere else. Okay, that's the embedding, one-hot encoding for H, one-hot encoding for E, one-hot encoding for L, one-hot encoding for L. Okay, now these are the inputs to the RNN block base network, the A thing that you've been seeing 2 slides ago. And each one is producing H0, H1, H2, H3. Okay, and these H's, actually, these are not H's. These numbers here are the H's. Okay, which need to be further transformed through the output layer to get to the appropriate output. Okay, for example, since our vocabulary is of size 4, we should have a distribution of over 4 characters, which means we need to produce 4 numbers on the output. Whereas the hidden layer only has, it turns out hidden layer we just chose to have dimension 3, so it's 3 here. Okay, so these numbers are produced to produce the output layer. There's a linear transformation going on. These numbers together, these numbers concatenated through the tanh yellow block produce another 3 numbers. Okay, and these 3 numbers are again transformed to get to these 4 numbers. Again, concatenated with the next 4, next 100 encode thing to produce 4 numbers and so on. Now these H's, see these outputs here, transformations of H's, basically linear transformation of H's. So they are supposed to now, each one should now correspond to a cross entropy term. Okay, why? This is because it's not a sentence classification problem, this is a language modeling problem. So we have actually 4 examples in that sequence, right? H should predict E, and HE should produce L, and HELL should produce this second L, and HELL should produce the final O. So there are 4 examples together happening. And so you'll have 4 cross entropy terms. In the first term, we just want to ensure that the second coordinate is the highest. Scores or transformed version of these scores are probabilities. The second number should be the highest. In this case, the third number should be the highest. Here in this illustration, it's not, but you want to make it high by changing the weights of your. The only thing you can train is the weights and biases of your the yellow tanh block, and also the output, this 3-dimension to 4-dimension transformation that's going on, right? So these green numbers are where where you're focusing on trying to make those numbers high. Okay, so hopefully this spells out everything that's going on in such an RNN model. Any questions here? Okay, no questions. I think this is just an explanation of that, so we will skip that. Let's actually look at some kind of code, because this is it's important to learn to reading documentation, and fortunately in this course we only have to look at one documentation most of the time, which is PyTorch documentation. So obviously you can use PyTorch documentation, you can use something like ChatGPT and so on to kind of further understand your thing offline, improve your thinking offline. So what is this doing, right? So it's just like NN.linear. It has a bunch of parameters. It has input size, which is literally the size of xt, hidden size, which is the size of ht that you prefer, number of layers. Okay, this is something that will come to later. It turns out that you can stack RNNs on top of each other, and so you can have multiple layers of RNNs, but we'll worry about it later. But by default, it's 1. Non-linearity you can change from tanh to ReLU. Somebody was mentioning ReLU. Bias is exactly the, in the tanh, do you want a bias or not? So it's true by default. Now this batch first is kind of important. It's going to become important in general while handling tensors. Okay, so while handling tensors, you might have to switch coordinates, as in make the first coordinate the second coordinate, the first coordinate. So there's some reshaping happening, and so there are some helpful functions like dot view, dot reshape, and then dot view, dot reshape, flatten. These are all functions that help you change the dimensionality of a tensor as needed. Okay. And then there's a dropout. You can do dropout with this because there's a linear layer, right? Bidirectional is something, it's an advanced topic, so we'll kind of defer to that. So defer that one and num layers later. Okay. And device, so far you've seen with CIFAR 10, you had to push the thing to TPU or GPU, whichever it was, and data type. Okay. So here you can see what the transformation is, right? So whatever we wrote. So it's basically, although we said concatenate and then apply a single matrix, it's the same as saying apply a matrix to xt, apply a matrix to ht minus 1, and add the appropriate biases. It's the same thing. It's just concatenate and apply a big matrix, or chop the matrix into half and apply 2 matrices to 2 different parts of the concatenated vector, right? So that's what this is. That's the transformation. So yeah, and the only detail that is kind of important for us is batching, right? So this n here, so it turns out the default input assumes that the batch index is the second index, okay, in this pre-built block that PyTorch provides. But if you prefer the batch index to be the first one, then you have to explicitly say batch first is equal to true. This is a potentially a cause for bad performance, right? If you don't know which one is the batch and which one is not, then it's not it's not appropriate. There are some other functions that we need to look at, padded sequence and pack sequence, but we'll see that at the end when we talk about hints for assignment 3. Okay, we'll see that later. So any questions about this? Yeah, there's some additional information. Yeah, it's very instructive to read it. Another thing that I wanted to mention is that this block actually does the for loop for you. Okay, so if your sequence length is 10, it'll do the 10 steps of your of your computation, like apply the A block 10 times. It'll do that for you, which means that its output, let's see, where is the output? Yeah, it has 2 outputs. Okay, so the output is going to be whatever is the number of steps. Okay, so if sequence length is L, then the output shape is, one of the coordinates is going to be L. Okay, so let's say D is 1 for simplicity. Then what is the hidden vector size? Hidden vector, the HT is, they're called hidden vectors. So hidden vector size times whatever is the length of the sequence, that's the output size. Okay, so it produces all the H0, H1, H2, H3, HT as this output tensor. And if you only want the HT, what is the last one, then you have to pick that one appropriately. Okay, if you're doing sentence classification. In addition to that, it also gives you just Hn, which is the last one, which is the same as in the output. So you don't have to actually have 2 outputs, but you can use the last one only. If you want only the last one, you can ignore the output and just take the last one also. Okay, so that's the function signature. And actually, if you click on source, you can actually see their implementation in PyTorch. Okay, it has a lot of comments on how things are. There's all comments actually. You can see a lot of decorators here. Yeah, I mean, I wouldn't say this is very easy to read in a single step, but you can see like what is happening, right? So yeah, I would not parse it right now, but you can see the function implementation. It's not completely like black box to us. You can see the implementations, as it's not that easy to parse, but nonetheless worth looking at if you want. Yeah.
Could you explain again how batched and unbatched input could affect and why?
No, I just meant that these guys, so they assume a default choice that batch first is false by default. So if you have if your first index is batch index, then if you're going to pass it through RNN block, you have to shuffle the batch index to be the second one, or you have to explicitly say batch first is equal to true. That's all I just meant.
What if you don't say true?
I mean, if you say batch, so by default batch first is false, and in case if you happen to have a tensor whose batch index is the first one, then it's going to be processed incorrectly. It'll think of something else as xt, whereas xt should be some other, it'll pick a wrong vector for xt's. So it'll process incorrectly if you don't set this batch first is equal to true if your first index is the batch index. So what I'm trying to say is, think of a tensor, right? In a tensor, let's say you have vectors for words, okay? Let's say you arrange the vectors for words such that the row index is the batch index and the column index is just the length of the vector, okay? Sorry, let me not say that. I don't think I explained it correctly. Let's say you have vectors for words, and it turns out in your batch, all sentences have the same length also, okay? And then let's say the batch index is the first index. Then the first batch, you have 10 vectors, word vectors, and each vector is of, let's say, also 10. Okay, so you have batch index 0 corresponding to 10 vectors, each vector length 10. Batch index 1 corresponding to 10 vectors, each vector of length 10, right? So it's just about, it's matrices at each batch, right? Now, what I'm saying is that cannot be the default input unless you set batch first is equal to true. Okay, so because if you're in that tensor, the first index corresponds to the batch. If you pick 0, colon, you'll pick the first batch, so first element of the batch. Whereas it's assuming that colon, 0, colon should be the first batch. Okay, it's a little bit different.
So it's confusing, but
yeah, I mean, it's hard to imagine this, but all I'm saying is it's just a question of which index corresponds to the batch, which index corresponds to the rows, which index corresponds to the columns of your data, right? So that's something you need to be careful about. They just shows this to be so that's why it's always good to go look at the definition. I mean, they gave you an option, right? You just explicitly say batch first is equal to true, then you're fine. You don't have to even think about anything more. Yeah.
So when we are dealing with batches, we convert it into true.
Yeah. I mean, no, if you deal with batches and your batch index is the first one, then you actually say batch index is my first one, so it's true. I mean, it just if it happens that in your case batch is not the first one, then you don't have to worry about it. Yeah. It's not for batch and not batch. It's in a batch setting, whether your batch index is the first one or not, second one. Yeah. So actually, there is a really nice tutorial. I mean, not tutorial. Yeah, you can say tutorial where they're classifying names with a character level RNN. Okay, so it's a given characters. They're saying whether the name is what are the different categories here? Scottish, English, Irish, and so on. Okay, so they have a sequence of characters, right? So names are not the same length. Everybody doesn't have the same length name, right? I have a really long surname, for example. So given you pass through, so for each character there's an embedding, and you get the HTs, and last HT you want to kind of map it to which of this 10 different potential origins the name is from. Okay. So, for example, the name Hinton, there's these are the scores. So maybe the lowest score means the highest probability of that category. So here they actually in this tutorial, this is just from tutorials intermediate thing. They show a lot of data processing steps. So how to work with characters, and we'll see some data processing steps towards the end when we talk about assignment 3. And more importantly, they actually show a lot of processing here, but they actually show an explicit RNN. They don't use the nn.rnn. So they actually say, okay, I'm going to have a linear layer. I'm going to have a hidden to output, which is also a linear layer, right? I have an input to hidden, which is a linear layer inside the RNN, right? So that's input size plus hidden size because of concatenation operation. And so they explicitly write how they explicitly write each step what happens with your computation. It's basically you concatenate, right? Tosh.cat. Exactly. In NumPy, I said H stack or V stack or whatever. So it's tosh.cat, and then combined thing is producing a hidden with an applying again, and linear layer is producing an output, and then you're softmaxing the output to get the probabilities. All right. So this is a very bare, like a very detailed implementation of RNN without using the NN.RNN module. Okay. So I would recommend looking at this. So what I skipped is basically all the steps before to get your data into this sequence of inputs and whatever potentially sequence of outputs. In this case, not sequence output situation. And this is going to be the bottleneck for your assignment 3 question 1. I can tell you that. So it's not the model definition. It's not the training. It's massaging your data to get to a situation where you can actually process it. Okay. So we'll talk about this towards the end. Yeah. Any other question? Okay. So if not, let's look at LSTMs next. So this model family is not too complicated. RNNs you saw, right? It's just one linear layer with one non-linearity. It's just all the understanding is about how to process variable length, which is literally apply the same function again and again, same layer again and again. Is a new thing that we saw. Now, inside the RNN family, there are actually many variations, and one of the variations, again invented in late 80s, perhaps it's called LSTM. Okay, so it's called an LSTM variant of an RNN, and we'll study its we'll study it because it's pretty popular. It has been used significantly over the past decade or so. More recently, maybe less popular because of transformer architectures, but pretty versatile and is able to do well in many situations. Okay, and many sequence modeling situations. So we already saw why we're looking at RNNs. It's to kind of persist, right? So connect past information to the current information. The question is, can they persist? Can such RNN architectures persist both long and short range information? Long range information means things that were like 20 words ago, 20 stages ago, and short range just means things that were like 1 to 2 stages ago. And the answer is, it's an empirical answer, but the answer is, it turns out vanilla RNNs are not that good. Although obviously the final hidden layer, hidden output, for example, does depend on the first input, but the dependence is pretty, weak in terms of it's not able to remember that information if it's needed for classification, for example, right? So for example, here, advanced prediction might lead to models. Immediate preceding words are helpful, but if you say, I went to UIC and after a lot of words, I said, I live in something, you want to predict that in your language model, then it's very hard to say, Chicago, if the words in between are like completely, all over the place, right? If they don't correspond to Chicago or anything like that, then it will be hard, right? So, and what we saw in the previous slide is exactly that. So if let's say H4 is being used to make a prediction, yeah, I'm not saying specifically H4. Let's say H3 is being used for something. All I'm saying is, if there are nearby X0 and X1 that are influencing the value of H3, let's say in the language model setting, each of the H's are being used anyway. We saw that in the illustrative example. So all I'm saying is H3 might be influenced by X1, X2, X1 and X0 if they're close enough, but HT plus 1, it getting influenced by X0 and X1 is very, it's empirically seen that it's kind of hard to influence it, because you saw that the A block is quite underpowered. It's just a linear layer with a non-linearity there, right? You could increase the complexity of that A block, the base network, but still it doesn't capture, is what people have observed empirically. And so they've invented a slightly different architecture. It's called LSTM, and there are actually many variations. LSTM is one example of a variant that we are going to study today. Okay, where the gap between the relevant information in the past, relevant information and the point where it's needed can become unbounded, can be arbitrarily long. LSTMs have been empirically observed to do better. Okay. And that's the origin of the name. Long short-term memory is just to kind of capture that. They capture both long and short-term, short-term recent events, okay, in the past. Okay, how do they do that is what we'll see. So now let's look at that. So the architecture is exactly the same. It's the A block, but now it has a lot more moving components. It's not too many. If you look at it, if you remember from our notation, there are like 4 linear layers, actually. Just 4 linear layers. It's not a deep neural network in any sense, because there are only 4 linear layers, but they're arranged in a certain way. And this leads to better capture of long-term information. That's the idea. So yeah. So what we're going to do in the next few slides is really spend time on giving an interpretation. This is all post hoc interpretation. We already know that this model works empirically well. Now we are post hoc interpreting like why the connections, what types of effects each connection could have. Okay, this is just post hoc justification. I'm just repeating it again. Okay, so let's just recap the notation. One extra notation is this pink circle, which is a pointwise operation. Pointwise operation just means if you have 2 vectors and if you want to do pointwise operation, it's just element-wise multiplication. So 2 vectors of length 10. If I do like this pink circle, then it's just v1, first coordinate times second coordinate, not times, but whatever is the operation, and second coordinate, whatever is the operation with second coordinate, and so on. Okay, element-wise operation. And everything else is the same as before. Okay. So, and as I said, we're going to have an interpretation to this network architecture. So the first vocabulary, some concept that we're going to introduce is the notion of a cell state. Okay, it's not really a state in any sense. It's just think of it as a vector. Okay, cell state is a vector, and we're going to give it a special name only because we think that this vector is the one which is capturing that long range information. Okay. What is that vector? That vector keeps getting manipulated on, as in like operated on again and again and again in each stage. But that vector is this top top black arrow that you see. So there's a CT minus 1, and that's getting operated on with 2 pointwise operations, and then that's getting out a CT. Okay. So just to kind of go back here, this network now has not just 2 inputs and 2 outputs, but 3 inputs and 3 outputs. Okay, so it's one extra output. Okay, that one extra output is actually the cell state. Yeah.
I had a question. So instead of doing the operation within the layer, why not we looking at the combination of HT minus 1 and HT outputs, and then probably doing an operation on them to find out the result?
Sorry, can you repeat?
So like here we are doing multiple operations within the
at each stage. So each stage is just the index, right? So T component of my sequence, T plus 1 component of my sequence. Yeah.
So my question is, why not look at the process? Why not look at a combination of HT minus 1 and HT, different combinations over the HTs?
Yeah.
And then look at the results.
Yes, that is a very good idea. Exactly the idea that was discovered or invented basically 6-7 years ago is the notion of transformer architecture, right? So that's what we're going to do next lecture. But for this lecture, we're going to keep it contained into the same block. Yeah. So yeah. So this vector, this additional vector that is getting operated on element-wise, it's called the cell state. It's just a vector which we kind of want to ascribe as like capturing long-range information. I mean, here we're just showing there's an HT minus 1 and XT, very similar to the base vanilla RNN. There's also HT, and same HT is being outputted. It's very similar to vanilla RNN, except there's a cell state. Okay, that's also being passed across stages. So it runs straight down through the unrolled network. That's why it's highlighted. It has very minor interactions except for pointwise operations, and in fact pointwise multiplication and pointwise addition going on. And it turns out information, so the third point, information could flow along it unchanged, just means that if there's a vector, let's say this vector is of length 5, okay, and there are 5 numbers, it could turn out that because even in spite of these operations, the output vector could be the same as the input vector. Okay, why is that? Okay, when can that be? Right, it can be if I do an element-wise multiplication with all ones. Right, if I multiply every coordinate with 1, then it's the same original number, and then if I add zeros, then I still have the same original number at every coordinate. Right, so obviously if I multiply with all ones and add zeros, then whatever is the input vector is the same as the output vector. Right, just giving an example of why information could flow unchanged. Information flowing unchanged just means that the input vector is the same as output vector. Okay. Now we're going to talk about how. So we want to think of the cell state as maintaining the important information needed for the model to make appropriate downstream predictions and whatnot. Okay, that important information therefore has to be added or removed from the cell state, from this vector. Okay, and we're going to do that through this notion of gates. Okay, gates, and so gates help us add information to the cell state. Gates also help us remove information from the cell state. Okay, through that multiplication and addition point-wise things that we saw. Okay, so what is a gate, right? So a gate is made of a sigmoid neural network layer and a point-wise multiplication. So this entire contraption here is called a cell. So it's called a gate. Okay, so a yellow box plus a pointwise element, operator. Okay, so what is happening, right? So you have a vector, and you have another vector here. This vector passes through a sigmoid operation, which means that the outputs are all between 0 to 1. Right, sigmoid is always between 0 to 1, and then you're doing an element-wise multiplication. Okay, that means that if we it could turn out that U is, let's say U is all like large numbers. Every coordinate is a large number. Then the sigmoid transformation, even after linear transformation, okay, let's say linear transformation doesn't change these large numbers, they still keep large positive. Then if you apply the sigmoid transformation, all these numbers lead to become ones, because sigmoid is like, large numbers become ones, right? And then if you do element-wise multiplication, V still remains V. Okay, so all I'm trying to say is that you can control whether V remains same as V or every coordinate of V gets attenuated. Okay, so for example, sigmoid, one of the coordinates of one of the coordinates here could also become, for example, 0. Right, sigmoid is between 0 to 1. Right, if you multiply 0 times the appropriate coordinate, then that coordinate of V becomes 0. Okay, so you're just doing element-wise multiplication. It's just that the multiplication is with numbers between 0 to 1. Each coordinate of this transformed U is just going to be a number between 0 to 1. So you can either leave the V unchanged, or you're deleting the V, whatever the number is, or basically making it 0. Okay, so that's an example of a gate here, which I just explained. So 0 means do not let the input through, so that coordinate will become 0. And if sigmoid leads to a 1, then that coordinate retains its value. Okay, so any questions here of what this operation is? Let's actually plug it back to our let's plug it back to our cell state and see how new information can be how information can be controlled in the cell state. Okay, so this was the gate. This gate can be used to forget old information in the cell state. Okay, what do I mean by that? So we can use the HT and XT, concatenate them, and call that U. Okay, so concatenate HT and XT, HT minus 1 and XT, concatenate them and call that U. Pass it through this gate apparatus. That will, because you have a sigmoid transformation there, it will going to produce numbers between 0 to 1. And then if you do an element-wise multiplication with cell state, you are enabling this operation of forgetting old information. Right? If some coordinate of the sigmoid output is 0, then you are removing you're basically setting that value to 0 in that coordinate of the cell state. And if the sigmoid output is 1, you are retaining whatever the value in that coordinate. Okay. So just to in terms of picture, HT and XT concatenated, pass through the sigmoid, that's a bunch of numbers between 0 to 1. If I do element-wise multiplication, I can forget old information. Okay, old information means whatever information was there in CT minus 1. Okay. For example, cell state may include, let's say, one of the coordinates of the cell state, for simplicity, illustrative purposes, includes the gender of the current subject. Okay. And this might be useful. This was useful for predicting the correct pronouns. Let's say we're doing language modeling. When a new subject is observed, you need to forget that gender of the old subject, right? So you can. I mean, I'm not saying that exactly how it happens, but you can actually ensure that that coordinate which captures the gender is now, you forget that information by multiplying it with 0. Okay, you could do that. And now we can forget information. Now we can actually add new information also to the cell state. Okay, and that's achieved through the element-wise addition operation that we're doing. So for that, we need two things. One is the original tanh layer, which is in the vanilla RNN. If you remember, we concatenated and we produced some new some tanh transformation that we call that new information, and then we're gonna use an input, another gate layer, to decide what values to put inside the cell state. So how does it look? Let's see here. So HT and XT concatenate, pass through tanh. This is exactly the vanilla RNN without, if you forget everything, all other things, this is the exact operation in the vanilla RNN. Now what we do is the same concatenation, pass through sigmoid, is now going to give us a gate which now controls which of this information should be actually added to the cell state or not. Okay, so you see that this multiplication operation is grayed out here, whatever is made transparent, but this is exactly the type of operation that you're seeing here as well. Okay, so new information was generated, or new vector was generated using the concatenation of HT minus and XT, except that we're using an input gate to regulate, which of the coordinates should actually still remain the same value, or should it be attenuated to 0, or should, basically, should it be attenuated or not? And once you do that, then that information is just added as is to the cell state vector. So cell state vector and this modified input information is just added together element-wise. Okay. Any questions here?
So basically, if you have the value of one variable, so it's fed into this model and it's generating some output, and at the end, just before you decide that if we want to add C of t minus 1 or not, that we have to decide that C of t minus 1 is basically some information from the previous value.
Not just previous, previous several stages.
Steps, okay. So if you want to add it or not, and then that plus
if you want to add new information to that or not, into the cell state.
And XT is your new information. It's totally new.
No, XT is new information, raw information. XT and HT minus 1 concatenated untransformed is the unmodified new information. Unmodified but transformed new information of XT. So there's a transformation, right?
Okay.
And with this input gate, I'm going to modulate it and then add it to the cell state. Okay. So it's as if like all new information not useful, but I'll first also modulate it and then.
So first model captures all the valid information from the new variable, and if it is needed, then that
this one captures the new information. C tilde t is the new information, but it's unfiltered, as in unmodulated. This part is like an input gate. So anything like looks like this multiplication and sigmoid, it's a gate, and so it regulates which information should be present in the output. It's a modulation step. Very similar to a sigmoid and a multiplication step, which is modulating what information should be retained here.
So C of t minus 1 is basically a X of t minus 1 information.
It's not. I mean, it's not exactly X t minus 1. It's like that.
X of t minus 2 like this.
So HT minus 1, C of t minus 1, they are outputs of the previous stage.
Previous 2 or 3 steps.
I mean, immediately previous stage, but they are influenced by all the previous computations. Yes. Any questions?
Like even in previous slide, HT minus 1 and XT, HT minus 1 and XT concatenation should have, after pass through the sigmoid layer, it should have similar dimensions as the CT minus 1.
Yes.
To
to kind of, this is just a gate to forget. I mean, to forget, you don't need new information, right? So to forget, you just have to create element-wise numbers between 0 to 1. So that coordinates where there's 1, you retain that information, retain that value, and whenever the coordinate is 0, those values are kind of are reduced. And it's not the zeros and ones. The sigmoids also produce numbers between 0 to 1, and they just get attenuated here and there. Okay. Just for adding new information, you do need not just the gate, but you also need the you don't need just the gate, but you also need to generate new information. That's why there's an extra. I mean, it's not extra. This is the actually core of the vanilla RNN that you're seeing here. This is exactly the same as the vanilla RNN's tanh linear layer. Okay. Yeah, and once you have C tilde T, you do input gate modulation, and then you add it to your cell state, add it to the vector, basically. So basically, for example, added the gender of the new subject to the cell state. This replaces the old one that we're forgetting. So you kind of make something 0. Let's say some coordinate illustratively represents the gender of the current subject. Then that coordinate you're multiplying with 0 with the sigmoid output, which is 0. And so it becomes a 0. And then this information is adding some new number there, for example, just as an illustration. Yeah.
So is it possible that we can feed the value of xt in both the layers? Means bypass the layer also and also extract some new information.
Where? Sorry.
Left one side and the middle, both all together.
What is the proposed change?
Xt and h of t minus 1 concatenate, and then it will pass through the bypass layer, that is simply a sigmoid function. No, left hand side.
It is being passed, no?
So first of all, it passes through that.
Yes.
And then it goes for the transformation.
No, I mean, it's being passed to all these inputs. The same thing. Yeah. It's just copies of it's just same information being passed. Yeah, this concatenation is going to a sigmoid. This concatenation is also going to another sigmoid. This concatenation is also going to tanh. This concatenation is also going to another sigmoid later. So all the changes are happening at the same time. Yeah. It's just passing the same vector, concatenated vector, to multiple transformations. Yeah. Multiple layers at the same time. Yeah. They're not. So HT and CT are related to each other. You'll see that HT is just a transformation of CT. Yeah.
Every input value is dependent on your previous output.
I mean, every RNN cell is going to take previously computed values and some new information and produce some information to be passed on the next stage, right? So that's just the nature of RNNs.
It's like time series.
Yes. So maybe I'll comment on time series models in a second. Since we are deep into LSTMs, let's not switch over to time series at the moment. But right after we kind of summarize this, we'll talk about time series. Yeah.
For the layers, how do we know what's the appropriate? I mean, we don't always know what's the appropriate size of the vector that should be.
No, I mean, all these vectors are like fixed size, and I have an illustration with two-dimensional example. I can show that image just to kind of reinforce all the concepts about dimensionality, at least. If you're concerned about dimensions, we can look at an example in a second. Any other questions? No. Yeah, this is just what I said. So basically, I mean, I didn't show this operation, but the forget part is just, as I said, delete some information. And once you modulate the new information, that information is added to the cell state. So now, therefore, you know the whole cell state, something got forgotten here and something got added here. Okay, so that's how you're kind of maintaining long range information. So if nothing got added and nothing got subtracted, then maybe some information that was generated in like the first stage is still maintained in the maintained and useful for the next for the last stage, for whichever future stage. Okay, the only thing left is now how do we generate the HT, because HT so we consume HT minus 1 and XT and we modulated the cell state. Now the only thing left is to kind of somehow make HT a some transformation of cell state. Okay, that's what we're going to do. It's a very kind of straightforward transformation. So what are we going to output? The HT minus 1. HT is just going to be some filtered or transformed version of some transformed version of cell state. That's all. Okay. In particular, there's going to be two operations, which it's written in text here, but I will just show the picture and mention it. So this was the cell state, right, which has been kind of made transparent. So again, we're going to use HT-1 and XT to create, pass it through a sigmoid layer to have what is called an output gate. Remember this, and the multiplication operation is called a gate, right? So we'll have an output gate, and then what we're going to do is whatever the cell state is, whether CT is, we're going to first pass it through an element-wise tanh operation. So we're going to basically squish the numbers to be between -1 and 1. Okay. I mean, that's what they defined. There's nothing huge intuition here. Element-wise, just do a tanh operation so that numbers are between 0 to 1, sorry, -1 to 1. And then do an element-wise, again, modulation such that, depending on HT-1 and XT and the weights associated with this layer, some numbers are set to 0, some numbers are left as is. Okay, some numbers get scaled down, some numbers remain as is. And then that, whatever is a modulated output, that's considered HT and also passed forward to the next stage. Okay, so just basically some modulated version of the cell state. Like first apply a nonlinear operation element-wise, and then just do a element-wise scaling up and down with each coordinate being multiplied with a number between 0 to 1, and then just call it a HT, and then pass it out and pass it as the future. So HT is just a kind of a byproduct of the cell state. All the action is happening in the cell state. Forget old information, add new information, and once you do that, HT is just some transformation of the cell state. Okay. Any questions here? No questions. Okay, so I know this is a lot of diagrams, but let's look at it as a summary. So we have the forgetting gate. We have the remembering or adding new information part, which is the gate, and also the creation of new information, which is the tanh block. And then once you have those two, then you actually forget and actually add, which is the modifying a cell state, like element-wise multiplication and element-wise addition. And then once you do that, for the creation of HC, you just do a slight modification on the cell state and pass it out as immediate output, as well as for the next stage. Okay, those are the 4, I guess, interpretations of the operations going on in this network, right? So if you really, okay, any questions here for the LSTM? Okay, so we'll look at the dimension thing in a second. I don't know if I have it. I'll come back to. Yeah, I have it in page. Okay, so let's actually look at the dimension thing. So here's an example with the dimension, right? So here it's not such a good diagram perhaps, but here is just showing if you have a 2-dimensional input, HT-1, a 2-dimensional new information, XT, then what happens? These two get concatenated. There's a 4-dimensional vector. These two get concatenated, 4-dimensional vector. These two get concatenated, 4-dimensional vector. These two get concatenated, again, 4-dimensional vector. So 4-dimensional vectors inputs to these linear layers, but transformations were defined as sigmoid, tanh, and sigmoid, right? And it's such that this layer is such that the number of rows of the W matrix, for example, has to be 2. Number of columns of the W matrix has to be 4. Such that you still create a 2-dimensional vector because the cell state is 2-dimensional. So 2-dimensional, element-wise multiplication. That's why there's a multiplication and multiplication here, right? So hopefully this kind of gives you a reason of like what's the dimension, and what's the dimensions of cell state and inputs and outputs. Yeah.
I understood that, but there you have defined it to be 2-dimensional.
Yeah, we have to define, right? We have to define the blocks sizes. Yeah.
So will that depend on the query that we have, or how will we select the appropriate dimension?
Oh, just like in the vanilla RNN, we have to define what is the input size and what is the hidden size, right? So here also we have to define what is the input size and the hidden size. And I don't know if it's an explicit cell state. Let's see, LSTM. Oh, this is a quantization part, not the Tosh.n or LSTM. So input size, hidden size, there's no explicit cell state size. I think they just choose it to be the same as the hidden vector size. Yeah, actually that makes sense, right? Also, because your hidden size is to be 2, and so you are kind of, these are element-wise multiplication, so your cell state has to be the same size as hidden state. So you only have 2 degrees of freedom. I mean, 2 things to choose, which is always the case. Even in the vanilla RNN, you have to choose the hidden size and the input size. Okay, so then let's actually look at, I mean, we'll not look at the detail at all. This was just to kind of show a slide that, okay, LSTMs are not the only popular versions of RNNs. There are also other things called gated recurrent units, which are also popular. I guess a little bit less popular than LSTMs, which have very similar, you can have an interpretation of what's going on in the network, which is at the bottom left, but we will not do that because one detailed forward pass is enough to kind of illustrate the point. So gated recurrent units are also used, interchangeably. Now, here's the idea about num layers. Num layers is equal to 1. You can actually make num layers is equal to 2, 3, 4. What does it mean? All it means is that this is num layers is equal to 1. Okay, this type of operation is num layers is equal to 1. But if you do something like this, where you kind of have another sequence of RNN blocks, and whatever the output is, you just consider as an input to the next sequence. Okay, then it's a num layers is equal to 2. Okay, and num layers is equal to 3. So what I'm saying is that the whatever h0 you produce, that's like the x0 for the next layer, next I guess layer of the RNN layer, and then that h0 becomes the x0 for the next RNN layer, and so on. Okay. So this is what is the num layer parameter. Okay. And there's also another parameter called bidirectionality is equal to true or false. Bidirectionality just refers to, like this input, let's say this is actually a word vector or whatever input, is influencing everything and eventually influencing HT, right? But this H0 is only influenced by this path. Okay, all these other computations, they're not influencing because see the arrows are all going out, right? So this x1 is not going to influence H0. Okay, x1 has no bearing on what the H0 value is. Bidirectionality just means that you also do the reverse computation, where you go from, you say, it's as if you're kind of flipping your input and saying, okay, if I pass through input this way, what is the H0? So you could say, okay, what if I reverse these arrows to go from right to left? Now H0 is a function of everything that has appeared to over here, right? So that's bidirectionality. Okay, so that makes sense for some situations. Some situations it may not make sense. Like for example, you're doing language model, you can't. Perhaps it's not a good idea to kind of use the future words to kind of predict the current word, for example. So there is some situations where it makes sense. In forecasting problems, it doesn't make too much sense. Okay, so we did that. I think we already talked about it. Yeah, so there is a lot of empirical work in justifying some of these choices. Okay, because there are a lot of choices that seem like completely ad hoc. And these are just canonical versions, and we can choose, like you said, like every stage you could potentially choose a new different nonlinearity if you want, right? So there are a lot of potential choices, but it's just that the canonical choice or the popular choice that people use currently and coded up as like a building block in PyTorch and TensorFlow use what we have seen in the class, but you can always modify. Okay. Now let's talk about training. We'll probably not talk about. Yeah. So training we'll not talk about, but I want to, before taking a break, I just want to briefly comment on traditional time series models, because they're also sequence models, except their sequence inputs typically conform to the first slide. So instead of slide 53, let's go back to this slide, right? So your time series models still belong to this category. Although it may look like, okay, maybe they belong to this category, but they don't, because they don't take variable length inputs. Okay, think of what is so I don't know how many of you have done a time series course before. Think of ARMA models, autoregressive moving average models, or just autoregressive models. Okay? Autoregressive models just mean look at the previous 5 values and predict the 6th value. And then while predicting the 7th value, look at the 2nd to 6th value. Okay. So that would be an autoregressive model of order 5. Okay. So those models are still take into account dependency across typically a time index. For example, predict the stock market, not stock market, the stock market returns tomorrow based on returns today and the previous 5 days. Okay, so you generally have like a moving window of like window within which whatever observations were made that would correspond to that would feature in your input vector representation, and that would predict the future returns, right? But generally they would still be considered as fixed input and fixed output. Okay, in the sense that if you learn the autoregressive, so let's say you learn the coefficients of an ARMA model of degree 5, then there'll be, let's say, 5 coefficients. But those are fixed. Okay, it's not like you can change the input to like 6 length and 7 length. Then where are the coefficients for the 6th and 7th term, right? So there are no coefficients. So that would be time series model kind of relation to this. So you could use LSTMs, RNNs for time series situations, except they're you're basically not relying on variable length inputs. Like you still have fixed length input, which is a special case. It's okay to have. It's like saying I have to do sentence classification, but all my sentences are of the same length, which is okay, which still works, right? So you can use LSTMs in the situations where you need where you're using time series models. Okay, except time series models have a lot more richer interpretability and all sorts of tests you can do. Which LSTMs are mostly you're looking at loss functions, training and test losses, and mostly predictive capability on validation data. And there is also interpretability aspect. We are not focusing on that. We did focus a little bit on the interpretability of word embeddings and CNNs, but we'll probably not talk about LSTM interpretability. We don't have kind of time for that. Any questions for this part? Okay, if there are no questions, let's take a break for 10 minutes. What I want to do after the break is we have done almost all the heavy material. So after the break, we're mostly going to be looking at assignment 3 kind of hints, which is actually related to the next section, which is mostly applications. Okay, so sentence classification, email auto reply, and things like that. They all can be done using RNNs. So we'll briefly discuss them. Okay. So let's take a break till 7:45. Yeah. I was just talking to him earlier. So basically, this is an example of a marketplace where they are basically, you can rent out your GPUs and you can also rent GPUs for training. So I think we just clicked on the pricing page here. So it's about 8 cents per hour for a 3060. So these will be faster than, definitely don't do anything on CPUs. But if you are like, if something works on Collab, you're seeing that your code is correct, but Collab keeps preempting your instance, and if you just want to run it for like a few hours, then I think one of these single GPUs, if it fits the workload, then renting it for a few hours and getting your training done or something equivalent is a good idea. It is not the only vendor. There's the one I've heard of, but yeah, and mostly I guess these are for inference and not training, but you can do training for small models. Yeah. Okay. The next quick comment is this one. I think you might have got an email, probably, but just people have not seen it. There's a workshop. I think a conference. It's the workshop conference on March 13th. So it's a networking event, and not just this event. I think I strongly encourage you guys to go to as many networking events as possible, as long as they're relevant, obviously. But it's good to kind of meet and learn from professionals and generally kind of get to know what's going on in the market I mean, in the industry, in the profession, and so on. Okay. With that, let's actually get back to our slides. We'll just discuss a couple of applications, mostly because they kind of help you thinking about, I guess, the second question in the assignment 3. The second question in assignment is related to translation. Okay, machine translation, which is about translating from one language to the other, and you're going to use an RNN model to kind of do that. Okay, so for that you need to at least appreciate what machine translation is. We have already briefly mentioned it, perhaps in the previous text intro to text session, but let's look at some examples. Okay. So sentence classification, we have seen it, so I will not discuss it, but basically a variable length input, which is the collection of words. Let's say we use word2vec to already convert them into vectors, 300-dimensional vectors, for example. And then you classify your sentence as positive or negative, or it doesn't have to be just positive or negative, but any classification that you can think of. So the second example is that of image captioning. Which can be achieved using RNNs. There are actually other models also, but we'll look at, since we've been talking about RNNs. So image captioning is a very simple extension to RNNs, but also captures the idea of decoding. So it's worth kind of looking at this slowly. So what we do is we're going to use a CNN to encode an image. And once you encode an image, you basically get a vector for the image. And then you can imagine, oh, once I have a vector for an image, all I have to think of it is like how to create vectors for my text, right? So, but we don't have text here yet. I mean, the input is an image, and so we only have one x. It's not x0, x1, x2, x3 yet. It's only x0, right? But we can use an RNN to keep generating one word at a time, like a language model. Remember a language model? We can, if we have access to a language model, then for a variable length input of words, we can always say what's the next word, right? Imagine the extreme case where our input is only one word, which in fact is not even a word, it's just the image embedding. Given image embedding, you can always predict a word. And given now the image embedding and the word, you can predict the next word. And given the image embedding, the word and the next word, predict the third word, and so on. Okay. So how do you do that? It's actually just a recurrent neural network. So let's actually show that, whatever the picture was showing, we're going to just slice it slowly. So first, this figure just corresponds to a VGG16 or VGG19 model, but any model which gets you to a image embedding, right? So you get an image, create its embedding, okay? Using AlexNet or VGG16 or ResNet18 that you've already done. Then what you're doing is essentially what we would call a decoding operation. Okay, it's important to. So this is the first time I'm introducing the word decoding as a word here. It's still an RNN, but it's basically we are sequentially generating an output. Okay, that's why it's called a decoding step. So we're going to first use this image embedding, and maybe we have an embedding for the start token. So now I'm also using the word token instead of a word. So start is really not a word, but let's say there was an embedding for this special symbol which says, okay, well, let's start generating words. Okay, so this image embedding and the start tokens vector representation together goes through and basically an RNN cell, and you get a vector as an output. Okay, what is this vector? This is the distribution over words in your vocabulary. Okay. So all that changes is that before we used to have hidden vector ht-1 and xt. Here we have xt, ht-1, and the image embeddings matrix here. Okay, that only operates one time, so it's really a one-time operation. And at the beginning, anyway, you don't have a hidden vector, so you can drop this and just include the purple one. Right. Yeah, I briefly wanted to mention another thing. There's a slight difference. So as I said, LSTM, nn.lstm and nn.rnn do the for loop for you. If you don't want to, if in case you don't want it, there's a LSTM cell. Okay. LSTM cell, which that's not the quantized version. this one. LSTM cell and RNN cell do one step of your operation. So if you want to have an explicit control on the for whatever the for loop, then you can call LSTM cell and RNN cell. So there's an RNN cell also, it's the same thing. It only does one step. Anyway, so if you want to do one step like this. So let's say you got a distribution over words. And then what you can do is generate a sample. You have a distribution, you do a sampling from it. We know how to do it using SciPy or even NumPy. Like you can create a discrete random variable with a custom defined probability mass function. You can sample from it, right? Let's say you got some word, and now you have a new, now you can continue with an RNN computation. Now you have the original image embedding, you have the start vector, and you also have the vector embedding for the straw word, and then you're trying to generate a new distribution of words. This can only happen sequentially, right? So that's why I'm calling it a decoding step, which we've not seen before. And then you get a distribution of words, again get a new word, sample from there, get the distribution of words, maybe get a new word, and in this very nice happy case, we are actually getting the right words: straw, hat, and end. Okay, but it's not always the case. You have to train your model, which means train the RNN cell blocks, whatever the parameters are, and also the transformations from the cells to the RNN blocks to the output layer. All those have to be trained such that you actually generate the right words. I mean, reasonably right, correct captions. Okay. Any questions here with image captioning? So it's a variable length output. Okay, so we have not discussed variable length outputs. We've been talking about sentence classification most of the time. So this is an essential part of a variable length output application. It's still an RNN, but you have to sequentially generate one output at a time. Okay, and so if you're doing machine translation, which is assignment 3's question 2, you take a variable length input, some source sentence in English, let's say, and you're converting into let's say Mongolian. You have variable length input, you capture all that into hidden vectors, the H0 to HTs, and then you are generating a variable length translation, right? So you're generating a distribution over that Mongolian language words. So that has to happen one at a time, and that's variable length also, right? So that will follow the same idea. In fact, whatever I just said, the machine translation is very similar to summarization, related to speech transcription, question answering. All these have the same type of feature where you have to have a decoding because your output length is variable. Okay. So auto reply, I mean, we've seen it, and actually the slides are a little bit older than ChatGPT revolution. So so anyway, auto reply is a variable length output. So basically the replies are here. So given this email, count dozen will be there. Sorry, we won't be able to make it. Are just auto replies generated by this app. So it can be achieved using RNNs, right? So there is a little bit of nuance in this decoding step. I mean, image captioning, the step that I talked about, that's what I'm calling as decoding step. And so there's a little bit of nuance. The first nuance is that actually first version is already probably not useful, because let's focus on decoding step. Let's say we condense all this information to some last hidden vector, and then we're using that hidden vector to produce the first word in my response. In the image captioning, we already saw how to use that response as an input and then generate the second word. So this is even worse than that. It's not even using the previous generated output to generate the next word. So let's not worry about this version. Let's look at the version where we do that. So this is exactly the image captioning part, where first you generate the word I am, and then you sample the word I am basically, and then you take that as an input, and then use all the whatever is the previous hidden vector and this embedding to produce a second word fine, and then use that fine as a new input, and I am fine to produce the next word, and so on. Okay, so this is just a decoding the same as before. And the left hand side is exactly the sentence classification type of situation, variable length input. You keep generating hidden vectors. Maybe you use only the last one. Okay, in this version. Doesn't mean that you have to only use the last one. In this version, we're using the last one. Okay. Any questions for this setting? Okay. So one of the issues that we should fix, I mean, there are a couple of issues we'll fix in the previous setup, where we just kind of joined the sentence classification type of a model to a image caption type of model, basically. One of the fixes is that you might be wrong with the first sample, and then you're completely off in terms of your response. Okay. So how do we deal with that, right? So, for example, I mean, we don't have to always word with the highest probability and use that as our first word. Like, for example, here, I'm could be the word with the highest probability, put that as the input, and then fine would be the word with the highest probability instead of a sample and take that as the input and so on. So you could do that, but you still may be off because you're being greedy as in you're just looking at the most probable word right now, and then you're kind of fixing that. So if the first answer is kind of off, then everything else would be off, is the consequence of this. So that's why we're calling this as a greedy strategy, or a myopic way to decode. Instead of that, this is a very old idea from signal processing literature and so on, is to kind of keep a cache or keep candidate decoded outputs. Okay, what do I mean? So, for example, you process the input, and now you're doing the second part, which is the variable length decoding, variable length output generation. Instead of just keeping the only one word, you maintain a collection of candidate words. Okay, so instead of like just the most highly probable word, maybe look at the highly probable 3 words. Okay, and then look at the next, given this 3 as inputs, look at the highly probable next word that can happen. Now, the problem with this is going to be exploding in terms of so many choices, so many trajectories. What you can do is retain only the k best candidate output sequence at any given point of time. So k as in, like, let's say you choose a value 10 or 3, for example. In the auto reply, for example, you saw 3 replies, right? Those 3 replies are because the first one may be most likely, but the second one is next most likely sequence. And how are you getting the sequence? What is meant by k best candidate outputs is just the probability of high times the probability of comma times the probability of next word, whatever. So probability of yes times probability of sure times probability of end, right? Where are we getting these probabilities? Is just exactly the output by the it's just the distribution over words that we get at every decoding step. So we are able to get probabilities, and so we can just multiply them as a likelihood of this output sequence, and so we can maintain a collection of top k candidates, so that if the only candidate that we start with is kind of off, its probability is going to decrease over time potentially, and so we'll surface the right answer. Okay, and this idea comes from signal processing literature. As I said, it's called beam search decoding. Okay, it's some name here, but it's a very natural idea. And even if you don't know this idea, you should be cognizant of this could be an issue, and any heuristic way to fix it is always appreciated. Okay, the next I think it's the same. Yeah, so next idea is called attention. So one fix is this beam search decoding to kind of not be off with respect to if we just happen to choose the wrong initial decoded answer, then we are completely off. The second idea is known as attention. Okay, so what is attention trying to fix? Attention is trying to fix an issue with this architecture that we saw a couple of slides ago, which is that although we're computing all these hidden vectors h0, h1, h2, h3, all the way to hn, only hn is being taken as input while decoding. Okay, what about all these h0, h1, h2, h3? Okay, can we use them? Because, for example, if I'm trying to say hi, how are you, and maybe while I'm trying to say I'm, maybe you is actually essential, and when you say fine, maybe how are you is essential. So all I'm trying to say is that maybe the last hidden vector is that's computed is not the only one that should be relevant while decoding. Okay, and so that is kind of solved using the notion of encoder-decoder attention. Okay, so what is attention? Attention is just an additional neural network. It's not a layer, but a bunch of neural network computational steps that help while decoding any specific word, help the network look at the hidden vectors, relevant hidden vectors in the entire input history. Okay, so that's all. So attention is all about while decoding any word, which hidden vectors do I need to focus on while decoding the current word? Okay, and it's not a manual thing. It's completely, it's just the nature of how we define that attention computation. That while training, we figure out when we're decoding something, some words need to be attended to, as in focused on. Some hidden vectors need to be focused on, and so that's learned during training. And then at test time, you attend to the appropriate hidden vectors while producing an output. Okay, so that's the fix for this issue of information bottleneck. Otherwise, the last hidden vector is not going to have, potentially, even with the cell state and all that effect, may not have the entire relevant information to decode a very long sentence, right? So if you have like a 20-line sentence in English and you want to create a translation of that in, let's say, German, it's not expected that the last hidden vector of fixed dimension, let's say 10 or 20, can help you decode all the words that are needed to translate. Okay, so we'll look at attention in a second. I think speech transcription is not needed. Okay, so I'll skip this last example because it's not really, it's not adding anything new. But let's look at attention now. Actually, should I talk about attention or should I talk about the... Okay, actually, let's talk about the assignment, because I feel like we're running out of time and assignment is due next week. So attention, I'll cover in the next beginning of the next lecture. And actually, it's actually conducive because we're going to look at encoded decoded attention in the beginning of next lecture, and also the notion of self-attention when we introduce this architecture called transformer architecture. Okay, which is the backbone for ChatGPT and Bard and Gemini and all that stuff. So let's actually switch our focus to some discussion about the assignments. Any questions here so far? Okay. So this is the syllabus. Yeah. So assignment 3 has two problems. One is language modeling problem, and then the other one is machine translation, or language translation problem. So the first problem is basically, the first point is easy. Simple Markov model is easy to construct. You have to just look at the conditional probability statistics. You compute that from data, and based on that, you can create a language model, right? So you can just look at previous two words. Given previous two words, what's the probability of any word happening? If you can compute that for all the potential words, then you already have a Markov language model. Okay, so in particular, it's suggesting using the torch text library, and it already has the IMDb data set that you can directly import. Now, the second step is to change the output of the model in this notebook called sequence LSTM simple sentiment analysis to now make an LSTM based language model. This is non-trivial because the notebook is doing a variable length input to a sentiment analysis. So basically a sentence classification. So it's just sentiment prediction. So it's variable length input to sentiment. Now to change that to a language model, what is a language model? It's a variable length input to a prediction over the next word, right? So it's a prediction over the next word. So you have to, so you don't care about sentiment data at all, right? So in your data set, which is the torch text IMDb data set, you don't care about the sentiment values. All you care about is to somehow process your data such that for every IMDb review, you have to basically, if the review is of length 10, you need to take, okay, first word predicts the second word, first two words predict the third word, first three words predict the fourth word, and so on. So it's a lot of examples. So you could do it a very inefficient way where given a sentence of length 10, you can produce a 9 input-output pairs, okay? And then it's just a variable length input and one word output prediction problem. So it's exactly like a sentiment classification problem, okay? You could do that. Or you could take the more efficient way, which is to, given a sentence, use all the intermediate hidden outputs, make them, do the output layer transformation, get the distribution over words, so that, as we had an illustrative example in our slide deck, for the hello character sequence, we had like 4 input output pairs, right? So similarly, a 10 length sentence will have 9 input output pairs. All of them you're evaluating at the same time. Okay, so that would be more efficient. But this code, starting code, is, since it's only doing sentiment classification, it requires that extra step of how to make it efficient. Okay, and then we'll actually look at that code in a second, actually, but we need to kind of discuss some choices, if there are any choices. The choices if they're made for n-gram, because here we did not even specify what is n, so you get to choose what is n. And for this model, there, if you're going to start with this notebook, there are some choices made, so you want to kind of discuss them or elaborate on them. Yeah, and the next question is just next point is just, how do these language models work? So you can see how they work, because you just build them, saying create a 20-word generated output, repeat it 5 times, and obviously you could, we are suggesting you should generate different outputs. So Markov model, it's all about sampling. If you sample, then you can generate different outputs. Otherwise, if you take the most likely word, then you'll get the same word again and again. Yeah, so that's the problem. So any questions about the overall problem, except looking at the notebook yet? Because I want to look at the notebook next, which is a specific detail, only because it kind of discusses how to process data, which is the hard part here. So for CNNs, there was literally no hardness there was some hardness in processing data, because you had to define data loaders and data sets. Here also there will be data loaders and data sets, except you have to kind of create indices for words. Okay, like you need to have a sense of, sort the words so that word, 10th word means, okay, index 10, so you need to look up the appropriate word vector and so on. So there's some processing needed. So we'll look at that notebook, which says file not found for some reason. Okay, we should have refreshed this. It's not interesting. No, this one is just, I thought I changed it actually. And this is supposed to be not RNN, but okay. So if this link is not opening, just go to examples and go to the recurrent neural networks. It's not RNN. I actually changed it in my, so I don't know if I pushed it, probably. I forgot to push the repository update. But anyway, this is the, instead of RNN, it should be recurrent neural networks, okay? So let's look at this notebook, which has a really nice details about how to process data. Okay, so it's actually the same data, IMDb data. Okay, so first of all, it's always good to, I think I told you, right? So debugging, so print-based debugging, and there's PDB if you want to use PDB, or if you use IDE, you can actually use breakpoints, and you can see all variables, all their sizes, and so on, if you use an IDE. On Collab, also has features for debugging. So I have not shown it to you, but you can try using those features, or, any Python environment generally has PDB as part of the standard library, so you can use PDB. So first thing, so let's say there's some split of data, train data set and test data set. So what are these data sets, right? So they are actually just lists of tuples, I think. So let's see. Yeah, so they kind of they pick the train data set and split it into 2 parts, into 2000 reviews as part of train, and 5000 reviews as validation. So first step is tokenization of the text. Okay, so you need to break your data into, so break your sentences into words, right? So here they have a very helpful a bunch of things going on, but you don't have to use exactly all this, but basically they are trying to split the words. So you could say, okay, why can't I just do dot split with a space and just get my words? They're doing some few extra things. They're dropping, weird characters, basically removing HTML tags, using lower cases for everything, removing emoticons, removing punctuation marks. I don't know why they're putting back emoticons, but anyway, at the end of the day, they're getting words. Okay, so you could, you don't have to deal with them. You can drop emoticons if you want, but in this example, they're doing these steps through what I call regular expressions. Okay, you don't have to learn regular expressions and all the complexity that entails, but if you want to use this tokenizer, you can go ahead. Okay, so that's why, in fact, this script is there for you to kind of rely on this pre-processing as much as possible. Once you have tokens are just, think of them as words. Okay, then you want to also create a vocabulary explicit. Here we are doing it explicitly. There are actually helper functions in certain libraries which let you create the vocabulary directly, but here's a simple way to do it, right? So you create a counter, and then for every row in the trained dataset list has a label, which is a sentiment, as well as a line. For us, we don't really care about the sentiment, so we can forget about this and don't process it. For every line, which is basically this really long review of multiple sentences potentially, you apply the tokenizer, which means you'll get the tokens, which is the collection of words, right? And then you just give those words to this counter, so that you actually know this counter is basically maintaining for all the unique words what is the number of times they appear, right? So if you look at the length of that counter object, then you know what is the vocabulary size. Okay, so and then you're sorting. You don't have to sort it based on the frequency. You can just sort it alphabetically if you want, but you're sorting the tokens in some order, and then putting them in an object which is basically an ordered dictionary. Okay, so that way you know which location corresponds to, so that your words don't kind of again rejumble up together. Okay, so what are we doing with this ordered dictionary, right? We just want to ensure that every word has a unique number, and it's the same number every time. Okay, so basically it's like a word to index converter. That's what we're building. Okay, and on top of that, so that's a sorting operation and creating an ordered dictionary here. You can sort in any way, doesn't have a frequency. And then you're creating, so TOSTEX has a vocab object, okay, which lets you create this dictionary. So this in this mapping from a word to a number, and number to the opposite direction, a number to a word. Okay, so anytime, for example, if you have a probability distribution of words, you're not going to have word and its probability, right? You're going to have 0 means 0.3, is 1 means 0.2, and so on. So you'll have numbers. And let's say you want to pick the word with the highest probability. So you obviously look at the index with the highest probability, and then that index has some number. Now you want to get the word for that index. You can just ask vocab, hey, give me the word for that index, and it'll tell you what the word is, right?
So is it like we are just sorting it based on the frequency and giving it a number based on the probability?
Yeah, but we don't really care about how we give that, whether frequency or not, but somehow for each word you need to have a number, and for each number you need to know what word it was. So you need both sides. So it's like a reverse dictionary and the dictionary you need to have. So that's what this vocab helps you do it. If you can do it explicitly also, you can just literally iterate through each word and say, hey, for each word here's a number, and for that, create a dictionary where that number corresponds to this word. So you can do that. Okay, so it has some helper functions like insert token. So we can insert a special token, and so this is going to become important. We did not discuss it during the lecture, but it turns out, it's very obvious that sentences are variable lengths. So our processing, so for example, if you want to, even for sentence classification, one sentence will have 10, one review will have 10 words, another review will have 20 words. If you want to do batch processing, then we'll have to add some empty tokens, some kind of dummy tokens. Okay, that's called padding. So that if you want to do batch size 2, then both sentences need to have some entries, right? Every location. So we'll have to put some sort of dummy tokens. Okay, so they're giving inserting the token and giving a number 0, and inserting another token called unknown for word 1. So why do you say, okay, you may say, okay, why do we need this unknown token? Is because the words in training for which we created the dictionary, there may be some words in test which were not there in the dictionary. What do you do with that? You map it to unknown and say, okay, this one is unknown, still tell me what's the sentiment, or still tell me the next word and whatnot, right? So anyway, so these are some vocabulary related operations. yeah, so for example, you can check what is the token for each of these words. Like this is an example. You can check what the index for this word is basically. So I would suggest rely on this code as much as possible to process your text data, because it's basically doing that for your IMDb dataset. So now once you have it, you can create a simple function which, given any sentence, tokenizes it, and for every token creates the index. So what you're doing is, for a sentence, you're getting a collection of numbers, which just correspond to the words number, words index. Okay. Here's a lambda function. So if you are new to Python, you can write an explicit function, but it's just a lambda function. We don't care about labels for your assignment question. I think I'm going too slow. And then device choice is fine. Now here's an interesting function. It's called collate. Okay, so collate is a function that is used for processing data. Okay, so when you get a batch, when you get a bunch of data points from your data loader, okay, so you can either directly get that. When you're getting a small batch from your data loader, you can apply a function to process the data before you actually pass it to your model. So remember, like in previous situations, you would have just gotten a batch and directly passed that as an input to your model. But if you wanted to do some extra processing, like doing doing the mapping from words to numbers and so on, you can actually do it in the collate function. Okay, so that's exactly what's going on here. Actually, for every in our batch, when you get it from the batch from a data loader, we actually just getting sentences. What we want to do is actually get the numbers so that we can actually pass it through our model. Okay, so that's why you can see that the function here, text pipeline, is being used here. Forget about the label pipeline, we don't care, but text pipeline is being used here. Okay, so our batch is still batches of words, sentences, basically. Let's say 5 what is the batch size? Let's say 2 batch size of 2, then 2 sentences. They're all still words, but we can't pass it to the model because they're not numbers yet. So we need these indices. Okay, so that's what's happening here. And this, and I would suggest, we don't have time to cover it because we only have 8 minutes, but I would suggest look at nn.utils rnn pad sequence to use the padding. Okay, so to use the padding so that the batch, if 2 sentences are of an equal length, you need to pad so that they, you can't just put zeros there. You can put zeros because we chose the padding token to have 0 as an index, but you will see that with this, you can actually get the right, like a uniform sized batch. Okay. Yeah, and then once you get that thing, you can actually send it to device just like before. We don't need labels anymore. You can send it to device. But now here's the thing, right? You need to build a language model, not really a sentence classification model. So the simplest step would be to be inefficient, where for each sentence, what you do is create those 9 length. So if a sentence is of length 10, you actually create a 9 input-output pairs, where the first word predicts the second word, first 2 words predict the third word, first 3 words predict the fourth word. Now you exactly looks like a variable length input and one length output problem. And so you can just use, you can call that targets as like labels if you want. And so you will have the same, you can use the same machinery pretty much. But if you want to be efficient, you can do that also. Okay, and if you Google or if you search on the internet of how to do this problem, they would probably do it in a more efficient way. But if you want to use this code base, if you want a gentler change from this, then you should do the simpler way, the more inefficient way. So this function collate batch, right? So where is it appearing? It's exactly appearing here. So when you sample a thing from a batch from data loader, previously in the CNN's case, we were not doing anything. The batch was literally the images, so we just passed the images in, and the images were all the same size. But now we want to get the numbers for the text and also, kind of make them the same size, pad them basically, and then pass it to them. Okay. So I hope this kind of clarifies. And I'm just suggesting that you carefully kind of look at the input outputs, get a feel for like 1 example, 2 examples. Then you can, once you understand this part, I think it's the training part is just same as like the CNN case. So yeah. So I will not discuss the other sections. Yeah, so they guys, so for sentence classification, they still do the NN. So we use LSTM. So LSTM, after LSTM produces some output, right? So let's look at the forward pass. So there's a lot of other layers that you would have seen, linear layers, sigmoid, and so on. Why did we get the indices for the words, first of all, right? So we have this NN.embedding. I don't know if you guys used it before. If not, NN.embedding is that W matrix. So we get the word index, for which we also are simultaneously learning the word embedding also. So it's not, so although I said X0, X1, X2 in our illustrative purposes in the lecture, we already said there were word embeddings for words. You don't have to, okay? If you don't have the word embeddings, just give me the word indices. I will learn the word embeddings together while learning the language model. Okay, so this is very typical in many code bases, where if you don't have the embeddings or the vector representations for the words, you can actually learn them together while training your language model or while training a sentence classification model. Okay, so I would highly encourage just run this sentence classification model end to end, be comfortable with it, then start making changes to build a language model. Okay, and the extra layers are just for, once you get the hidden vector, then you can do a few more transformations before getting the output. That's all that's going on. Yeah, I wouldn't pay too much attention there. But yeah, so, and then in their case, they have binary cross entropy loss. For us, it's not binary cross entropy loss. It's going to be regular cross entropy loss, because we have vocabulary size as the number of outputs. Okay. I mean, you can change these things to whatever you're comfortable with in assignment 2. Okay, so this is just, and then once you train it, you can just, here they're just classifying something as positive, negative. You have to just generate a sentence in this question. Any questions for this? It's very exciting, but also non-trivial, I would say. It's not a one-word change. I know that even in the assignment 2, question 1 with the CIFAR 10, it was not a one-word change, because CIFAR 10 data set is different from ANDs versus Bs, and you had to also change the network a little bit. It's very similar here, but don't get stuck in the data pre-processing step, because at least if you can get the data pre-processed, then you can worry about like the model and training and those types of errors. Okay. The second question, there is no, as far as I know, there is no. Okay. Wow, I think I did a mistake here. Let's go back. The second question is, it's instead of language model, you have to get a variable length input output model. There is a link here. You can see how it's structured. Okay, so this actually is again, oh, I forgot. Oh, what I did is I think I changed this link to the other link. So, okay, let me go back and fix this. That's why I'm seeing why it's referring to the recurrent neural network problem, which is the thing we just discussed. But here, what you need to do is download a, not this one, download a language pair of your choice. I think here there's some examples of language pairs. So you can pick any one that you like to train on. And given that language pair, you just have to process exactly the way we processed one of the language, right? So we process IMDb text. Here it's the same thing, but you have 2 different texts to process so that you can match vocabularies to numbers. And so that way you can go from one language to the other language and so on. Okay. In fact, this second question is non-trivial, because we have to also do the opposite, I believe. Yeah. So we have to go from one language to the other, and also go from the second language to the first language. Okay. So if English is a language, it's a little bit easy. Okay, it's not a little bit easy. If English is a language, then you at least have globe embeddings for your language. But globe and Word2Vec are not there for other languages. Okay. There are other pre-trained word embeddings like fast text if you want to use them. So that's why make any assumptions as necessary. If you want to use fast text, you can, because fast text has embeddings for other languages if you want to use them. Okay, so there are some choices to be made here, but this is exactly the same model as question 1. except variable length output. So you have to do that decoding. So one step at a time. Okay, that's the only difference. Let me fix that link. I was supposed to fix that link for here. Instead, I fixed it here. So I'll just change that back. But it's 8:30, so I'll stop here. And if you have any questions, let me know.